Okay, now it's recorded. And let me briefly introduce our speaker. And Professor Wood just joined our school in the beginning of this year, and his research interests include non-Euclidean statistics, especially directional statistics and statistical shape analysis, asymptotic theory and methods, inference for stochastic differential equations, aspects of computational statistics, and applications of statistics in the sciences and medicine. So Professor Wood is a former joint editor of Journal of the Royal Statistical Society Series B and a current associate editor of Biometrica. So now let us welcome his talk about approximate likelihood methods for stochastic differential equation models with high frequency sampling.
Well, thank you very much for the invitation, Tao, and for the kind words. Maybe I should take this opportunity to say that it's sort of great to be back in Australia, even if these aren't normal times, but it's certainly very nice to be back. All right, so so I'll say a few words. Yes, that's it. Yeah. So I'll say a few words about the structure of the talk. So this is about sort of inference for SDE models. The main idea is to combine an Ito-Taylor expansion with what's called the epsilon expansion to enable one to use approximate likelihood methods. So I'll be saying more about that in a minute. But first of all, I should mention the co-authors and collaborators. So Simon Preston at Nottingham. Well, Simon was what was called a statistics mobility fellow, and this was a sort of program set up by the UK Research Council EPSRC to try and attract applied mathematicians and pure mathematicians into to statistics. And I'm pleased to say that Simon was one of the success stories. We had to specify some topics we would work on, and one of them was shape analysis, and the second one was stochastic differential equations. And and Simon has a background in differential equations, so that seemed a good topic. And then some years later, we had we shared a PhD student, Philip Payne, and he so we made some progress, but to cut a long story short, neither Simon nor Philip have time to work on this in the near future, but fortunately, we've managed to get Kevin Liu involved from RS fans, and so the current situation with this work is that we're preparing a revision for the Scandinavian Journal of Statistics. So with Kevin on board, I hope we'll be able to wrap things up fairly quickly. Okay, so let's say a few words about stochastic differential equations. So BT is a Brownian motion. So I'll say a bit more on the next slide, but we can think of mu as being the drift, sigma as the diffusion coefficient. Yeah, and they'll be assumed to be fairly smooth. Yeah, the way to interpret one for those not so familiar with SDEs is to think of it in terms of the integrals on the right-hand side. So, the first integral on the right-hand side can be thought of as something like a standard integral, but the second integral is a stochastic integral with respect to Brownian motion. Yeah, so that's a sort of long story, but we don't really need to worry too much about that. For those of you not familiar with SDEs, I think probably the one helpful thing to bear in mind is that when the process is at small xt at time t, and h is a small time increment, then the jump of the process will be normal with mean and variance as shown in Formula 2, and so in other words, the drift function evaluated at xt and the diffusion coefficient evaluated at xt, and and both of these are multiplied by the h. So I hope that gives some sort of intuition of sort of how to interpret interpret Formula 1. Now we're mainly interested in doing inference for stochastic differential equation models. So we put a parameter theta into to the drift and to the diffusion, and what we'd like to do is to estimate theta and to do the usual sorts of things. The one does with likelihoods. So take a simple concrete example. If we take mu to be a constant times x and sigma to be a constant times x, then we end up with geometric Brownian motion. By the way, I'm happy for people to ask questions during the talk. So if anything's not clear, please feel free to interrupt. Right. So one important property of the SDEs, which I've the one which I've written up, and that one, they're Markov processes. So what this means is that if we know the transition density, so in other words, we know the conditional distribution of xt plus h, conditional on xt, and suppose we observe the processes at times t1 through to tn, then using the Markov property, we can just write down the likelihood in this simple form. So so whenever one has a Markov structure like this, then it's then once you have a suitable model, then it should be fairly easy to write down the likelihood, and then you can use the likelihood for estimation and so on. But the problem for SDEs is that that for nearly all SDE models, the transition density is not known in closed form. So so it's not so so it's going to be hard to use exact likelihood methods. Yeah, now I should say this problem has been around for for a while, certainly since the 1980s. So certainly since the 1980s, people have been thinking about this, and I'm sure if you look hard, one can also see traces in the 1970s as well. So I should just mention some of the important work. So this first paper, this is one of the earlier papers, and one of the interesting things in this paper, they have an explicit representation for the transition density using what's known as the Gerstenov theorem, and I'll be saying a bit more about that later. And then there are and there's a nice some nice work in this the 1992 paper where there's a central limit theorem for an approximate maximum likelihood estimator. So that's using an approximation to the likelihood. There's also a nice paper by Kessler where he proposes a Gaussian approximation to the transition density, but with accurate approximations to the mean and variance. So and I'll be saying a bit more about that later. And then a bit later on, there was there's a whole series of papers by Eitzer-Halia, and certainly the earlier papers in this series, they so basically he approximates the transition density using using Hermite expansions of the transition density, and he also looks at small time approximations. Now there were the papers by Eitzer-Halia. I mean, they aren't easy reads, and I think there were a number of issues which weren't completely clear, and some of these were cleared up very nicely in this paper by Chang and Chen. But but even so, I feel as though these papers are quite sort of complex, and I think there's sort of scope for developing sort of alternative approaches. So that's no criticism of these authors, but I think so what I'm going to do now is to explain the approach which that we've taken. So the first of the ingredients is what's known as the Ito-Taylor expansion. So the SDEs of the form shown here, the XT process will, so under reasonable conditions on A and B, the XT process will be a continuous but not smooth. So one can't develop a Taylor expansion in the usual sense. But it turns out that that using Ito's formula, there is a way to do sample path expansions. So let's have a look at the basic idea. So so supposing f is a smooth function, then it turns out, so using Ito's lemma, that one can write write ft in this form where the L0 and the L1 so these are differential operators which operate on the f. So so the a and the b are the drift and diffusion coefficient, and these are and these partial derivatives, first and second partial derivatives with respect to x. And so one can use this, and what one can do is to repeatedly to approximate the integrands using using these differential operators. The number of terms grows fairly quickly, but it leads to an expansion. And the book by Cloden and Platen, that's got that has a huge amount of information on these expansions and and so on. So this is a way to approximate the xt. So so applying that to the SD that we're interested in, well, let's first of all simplify things by just focusing on the case where we have the drift mu tilde, but let's assume that the diffusion coefficient is 1, and we'll see how that can be handled later. But so we end up with an expansion that looks like this for the so this is yt here, and where so each term so we have these c's, well, and we have the i's. So what do the c's and the i's look like? Well, the c's are so these are just derivatives which are so they're derived using the operators L0 and L1. So we end up with so these are all y derivatives. We're not doing anything with theta at the moment, and so all of these c's are sort of simple functions of derivatives of well, the drift mu tilde. And the i's are integrals with so the integrals which involve the the Brownian motion that's driving the SDE, and so there's something missing from here, I think. So I think there should be some extra terms.
Triple integral. It should be a triple integral.
Yes. I've left. And that should be a double integral. So so I'm afraid I've left some. There were some typos here, I'm afraid. But yes. So no, the first one is correct, but it's the second one that
It should be simply ds.
Yes.
At the end.
Yes. Yeah, that's right. Yes. Thank you. Right. So we have the Ito-Taylor expansion. And what we want to do now is to see if we can somehow use that to get a higher order approximation to the transition density. So so I'll say a few words about the epsilon expansion, or at least how it can be derived. So let's suppose that we have two random variables, x0 and x1. Yeah, and we have an epsilon here. Yeah, and the epsilon, yeah, so we should think of the epsilon as being small. Yeah, then how should we expand the distribution of x, well, in powers of epsilon? Now, first of all, in the special case where x0 is standard normal and x1, well, x1 is and x1 is independent of the x0, then then it turns out we end up with the classical Edgeworth expansion. Yeah, and the cumulants of the cumulants are determined by the cumulants of x1. So that's in the situation where you have x0 and x1 independent. Yeah, but what happens in the general case where they can be dependent? Yeah, well, let's consider a slightly more more general situation, which will be appropriate here. So if we think of there being several epsilons, and the x is on the right hand side, there's no assumption that they're dependent. And let's assume that the x0 is standard normal. Then it turns out that so we're writing conditional moments here for the xj's as a conditional on x0, and the product of xj and xk conditional on x0. Yeah, and then it turns out that we end up with an expansion that looks like this. So this is the expansion which is linear in the epsilons. Yeah, and if so we can see the Hermite polynomials coming into it, but we also have the conditional moments and derivative, the first derivative of the conditional moments, and when we take the linear and the quadratic terms in the epsilons, then we end up with something like this. So one can see that there's lots of structure here, and in fact one can write down the general term. So there is a bit of work that's needed to collect terms in the appropriate order. I'll sort of show how to apply this to the case of interest in a minute. But but the epsilon expansion, that's actually due to Cox and Reed. I've never seen it anywhere else. And that's for those of you. Some of you may remember the Cox and Reed paper, the Series B red paper from 1987. Well, this is not that paper. This is the other Cox and Reed paper from 1987. I think it was published in the Canadian Journal of Statistics, and they have this expansion there, and they use it for various purposes. But but one thing to note, although it's a nice looking expansion and not hard to derive derive heuristically, it's actually quite hard to check its validity. And certainly in the situation we're in, it's hard to check its validity. So we used a different way to check its validity using the Gersdorff representation of the transition density. So So I'll say a few words about that. So before doing that, it's worth just mentioning that in the one-dimensional case, there's a transformation that you can apply, which it transforms to what's called a unit diffusion, where the diffusion coefficient is 1, and this has been there were various advantages to doing this. It simplifies simplifies many of the formulas, and also it seems to lead to greater accuracy for at least more efficiency. So in that that you need fewer terms to get comparable accuracy. So what we need to know here is that we have a transformation to the unit diffusion, and then and this is the Gersdorff representation of the transition density. So so the first term here so the first term is Gaussian. Then we have the second term, which is well, that's an integral. The second term is an integral of the drift function, and then we've got this third term, which is the expectation of a certain functional of the Brownian bridge. So the Brownian bridge is tied down to be 0 at both 0 and 1. And G is this function which depends on the drift function. So so under suitable conditions, one can control the remainder term when you expand this for small h, and so using that, you're able to justify the epsilon expansion sort of indirectly. So that's how we did that. So let's say a few words, some conditions. So we've assumed that the diffusion coefficient is bounded away from 0, and that the the drift function and the diffusion function, that they and low order derivatives are bounded. And then so it's slightly confusing because we're working on different scales. So the x. So the x here is the original process, the one that we actually observe. Z is defined in this way, and we've also got the y, which is the transform. So that's obtained by transforming the x process to the unit diffusion process. And the reason why we need to keep these three things in play is that the density actually involved. So what we're actually interested in. So we've standardized the z so that it's of order 1, and but the right-hand side we need to make use of the y's. So so. But so this is the approximation to the transition density. This is up to and including delta squared terms, and these are the C's from before. And these the H's are Hermite polynomials. So if we wanted to take more terms, we could, but probably without good reason, we probably wouldn't want to go beyond this. So that's the form of the expansion. But then there are also some quite strong uniformity results which can be derived for the approximation to the true transition density. So under the assumptions mentioned earlier, we can get these, and we can also so we haven't so we haven't talked about theta derivatives, but one can also get similar results for theta derivatives, but under stronger assumptions. Fine. Okay. So one of the questions which intrigued me for a while. So I mentioned the Kessler approach, where he will develop a Gaussian approximation to the transition density, but using accurate approximations to the mean and variance. And one of the questions which has intrigued me, to try to quantify what one loses from making the assumption of the Gaussian density, and it turns out it's not so easy to be very precise about that. Well, so intuitively, one would think that one loses from not taking account of skewness or other kurtosis. That's where one would lose from using the Gaussian likelihood. But even with that sort of insight, it's not so easy to quantify. But we have come up with one result which looks at how close the estimators are to the exact maximum likelihood estimator. Now we don't, so we don't actually calculate the exact maximum likelihood estimator, but conceptually we can think of it as existing. And now one thing I should mention here is that we've now separated theta into an alpha parameter and a beta parameter. And one of the reasons for this is that the alpha and the beta actually have different rates of convergence. So, and this sort of makes sense. But were you to have the same parameter in both of them, then the rate would be determined by the sigma rate. But I'll show that in a minute. So the subscript k here means the Kessler estimate, the Kessler estimator, and the epsilon one that refers to the estimator based on the epsilon expansion. Now it's a bit complicated to completely unravel this, but I'll just say that basically two situations arise: either the rates of the Kessler estimator or the rates of the Kessler estimator and the epsilon expansion estimators are the same, or the convergence rate is faster for the epsilon expansion. So where they're the same is when you get the same thing here, but then once you move down, you get delta to the fifth here, you get delta to the seventh here. But that's sort of the best that we've been able to do as far as sort of quantifying theoretically what the improvement is over the Gaussian estimator. So I think it's a bit surprising that it's sort of so hard to unravel. Maybe someone else has some ideas, but so that's the for the alpha parameter, the one in the the drift function, and the rate here is n times delta, where the delta is the width between observation points and the n is the sample size. But for the diffusion coefficient parameter, one actually gets standard rates of n to the half. But but what's going on here is roughly similar. But so as you move down, you get delta to the fifth here, and you get delta to the seventh here. So it's sort of a slightly murky story, murkier than I would have expected. Fine. Fine. So I'll say something about some numerical results now. So the so the epsilon one, well, that's using the epsilon expansion, but leaving off the non-Gaussian terms in the expansion. And so this is actually close to the likelihood that Kessler used. And the epsilon 2, that's the approximation that we talked about in the talk. The AS1, that's the first order rates of Hollier expansion, and then we got the AS2, and that's the second order. So so we are going to be doing more more numerical work for the revision, but I'll just show some of the examples here. So for this, so the delta here, which is the width between sampling points, is 1/12, and we've got so this is for this is deriving different approximations to the OU transition density, which is known. So we can calculate the exact. And so it pretty much looks like one thick line. So they're all doing pretty well here. And similarly for the so CIR, so that's Cox, Ingersoll, Ross. So that's a particular SDE that's that's quite widely used. And once again, so for this particular example, there's not much difference. One of them's breaking ranks here. That's the AS1, but all the other ones are very close. So yeah, but that's one of the things we want to do, is to do some more extensive numerical results and look at some more challenging examples. Yeah, and then when we look at some numerical results, so this is for the OU, and so the first column is for the exact, because we know how to calculate the exact maximum likelihood estimator. But then the second, third, fourth, and fifth, these are all so these are all looking at differences from the MLE. So we can see that the epsilon 2 and the AS2 tend to do better than these. I think so they tend to do better than the epsilon 1 and the AS1. The honors are sort of shared, I think, between epsilon 2 and AS2, the epsilon 2 and the AS2. That's the Etzahalia 2 approximations. I think there's not uniformly one that's superior. I think it's roughly similar here. So and this is also the Cox, Ingersoll, Ross. So I think it's I mean I think it would be hard to come up with something where that's uniformly the best, but I think they're in the same sort of ballpark anyway. Fine. So one or two points for discussion. So using so applying the epsilon expansion to the Ito Taylor expansion, it leads to a good approximation to the likelihood, which is easy to implement and faster compute. And I think it's in the same at the same ballpark as existing methods. One challenging question is to try to extend to the situation with multidimensional SDEs. That's I think that's sort of reasonably challenging. I think one of the reasons why it's challenging is because of the in the multidimensional case, there's in general no transformation to a unit diffusion. And related to that, I think there's no so first of all, that means that one needs to take more, to include more terms to get a certain level of accuracy. So that's one issue. And and I think there's also so in general, I don't think one will end up with such a nice a representation for the transition density either. So it is more challenging, but but it's something that there might be that it's something which I've thought about, and I think it would be interesting to see what can be done. Yeah, and finally, so we didn't have any real data, but if there's anyone who's that works with data for which SDE or related models sort of might be relevant, then I'd certainly be interested to talk about it. Right. Well, I think I've that's well, that's pretty much all I have to say. But well, thanks very much for your attention.
Okay, let us thank Professor Wood for his very interesting talk. So any questions or comments?
Yes, I like to make some comments. I'm Eckhart Platen, so the Ito-Taylor expansion is going back to my work 30 years or more ago. So I'm very pleased to see Andrew now at ANU, where I also spent quite some years and actually working on Ito-Taylor expansions at that time there. I'm still an honorary professor at your department here, so it's very nice to see. And I'm still interested also in the estimation of SDEs, discretely observed diffusions. It's very interesting, and I would have some papers I can send Andrew if he wants to, and have discussions. This is just what I wanted to say. Thank you.
Yes. Well, well, thank you very much, and I would be interested to receive those papers. So thank you very much for your comments. Yeah.
Any more questions or comments?
Maybe me, I'm Spiridon Penef. Hi, Andrew. We have met many years ago. Just a question. You were relating your method to the Kessler method, and it's not sure. I'm not sure whether you consider the Kessler method as a particular case of what you have done, or it's kind of not related. Because when you were speaking about your epsilon 1 method, you said that it is close to the Kessler, but you didn't say that it's the same method. So what is actually the difference? To me, it seemed that kind of your method is an extension of Kessler's. Is this true or not?
Yes, I think when you include the non-Gaussian terms, then it's maybe I should be a bit clearer about what I mean by the non-Gaussian terms. Let me see if I can. No. Let's go to. Sorry, let me just find this. So the non-Gaussian terms are those where the subscripts include more than one. So more than one. So for example, that's a Gaussian term, but that's a non-Gaussian term. That's a Gaussian term. That's a Gaussian term. That's a non-Gaussian term. So so when you only collect the Gaussian terms up to a certain order, then that's going to be similar. The same as Kessler's method. So modulo how you collect terms, yes, that's a way to think of it. So one way you can think of it is as an extension of Kessler's method. That's correct.
All right, thank you.
Fine, thank you. And Yeah, well, nice to hear from to hear from you to hear from you as well. Yeah.
Professor Wood, so there is a question in the chat from Robert. And the question is, you mentioned on the last slide about inference. So does your approximation allow for inference on the theta MLEs?
The theta MLEs. Yes, I mean, yeah, I'm not quite sure what the question. Yes, I mean, so yeah, so we're constructing an approximate likelihood for theta, and so yeah, and so one can use that likelihood for approximate inference on theta. But I'm not sure if I've quite understood the question.
So Robert, if you want to, you can directly unmute yourself and maybe ask more.
Hi. Actually, it was Francis's question. We're both watching in my office, but I think that makes it clear.
Yeah. So maybe I didn't make it sort of completely clear, but what one's doing with these approximations to the transition density is then to make use of where is it? To make use of formula 3 for the likelihood for theta, and then to use the approximate likelihood for theta, well, for estimation and so on. Does that make sense? Yeah. Okay.
Any more questions or comments? Professor Wood, I have a really brief question about your approximation. So based on my understanding, your approximation, I think, is also valid only when the h is very small, right?
Yes.
So it's kind of very similar to Yasin Azarhalia's small time approximation. I mean, they also need h is very small.
Yes. It's a small h approximation. That's right. Yeah.
And my the other question is about the quite practical, because I tried Yasin Azarhalia's approximation years ago in real practice. So because we kind of used approximate density, so it's not a real density. So sometimes, so even though in your plot it shows that they kind of approximate very well, but sometimes in real practice, especially when h is a little bit large, sometimes we will have negative value for the density, such that in real practice, when we consider maximize log likelihood, so we will have some invalid values for log likelihood in real practice. So do you find some similar situations in your numerical studies?
Well, that's a very good question. We've only found it happens very rarely. I mean, but yes, it certainly can happen, and there are ways to modify the approximation. But I think it hasn't happened with sufficient frequency for us to think about actually changing the approximation. But if in some situations that were to happen, then I think one could set up the expansion in a different way. You could do it, for example, inside the normal density, in such a way that, so I think that would so that would be something that I would think about if it were to happen frequently. But it's certainly something to be aware of, and potentially it can happen. So that's a very good question. Yeah.
Thank you so much. So any more questions or comments?
May I ask a very practical question?
Yep.
Yeah, so I'm just wondering, I'm not familiar with all the estimators that you've mentioned in this talk, but I'm just wondering, we're taking these Taylor expansions to estimate parameters ultimately. And I'm just wondering what the virtues of this Taylor expansion-based approach is over, for example, a Monte Carlo gradient estimate. So if we simulate a bunch of trajectories and differentiate through our solver to estimate parameters, which seem to involve a lot less collection work. Yeah.
Yeah. Well, I think. Yeah. I mean, I'm not sort of. Precisely familiar with. Using simulation-based approaches for this, but I would think that it's quite challenging to get them to work. But I'm not sure. But so. Yeah, so I think if one can do things that are based on analytic approximations, and I think with the proviso that they work, I think it's an order of magnitude easier than doing things which are simulation based. But then maybe I'm showing my viewpoint. So I have an open mind. I mean, if simulation-based methods can be shown to work very well, then why not? But I think it. But I think it's not something that will be so easy to do. But actually, now that I think of it, some people have tried things something along those lines. I think there's a paper by Durham and Gallant. That was written a while ago, where they've sort of tried simulation-based things. So, yeah, so maybe it's worth looking into it, and I have an open mind. But I think it's, but I think it's likely to be quite challenging to get it to work. But I'd be happy to be proved wrong.
Okay, sure, cool, thank you.
Yeah, okay. I think thank everyone for their questions. And so if you want to chat with Professor Wood more, so in the end, I will leave a short period of time for this Zoom opening, so you can chat with Professor Wood a little bit longer. So now let me just end today's meeting, and thank you all for joining this Zoom seminar. And next week, we are going to have Associate Professor Nicola Armstrong from Perth to present. And since the speaker is at Perth, so the start time is also at 12 p.m. At Canberra. So the notification has been sent, and please take care and stay well and safe. And see you next time. And now I'm going to stop recording, so feel free to chat more with Professor Wood.